Heisenberg's Uncertainty Principle, introduced by Werner Heisenberg in 1927, was one of the most revolutionary ideas in the history of physics. It challenged the deeply ingrained beliefs of classical mechanics and introduced a new way of thinking about the universe, particularly at the quantum level. Prior to Heisenberg's discovery, it was assumed that with enough precision in our measurement, we could determine both the position and momentum of any particle at any time. This idea was in line with the deterministic nature of classical physics, which suggested that the future of a system could be predicted if all its initial conditions were known. However, Heisenberg's uncertainty principle directly contradicted this belief. It stated that certain pairs of physical properties such as a particle's position and its momentum cannot both be precisely measured at the same time. This was not due to imperfections in measurement tools or the observer's limitations, but rather a fundamental characteristic of nature itself. To understand the significance of this idea, it's crucial to grasp the key concepts of quantum mechanics that were emerging at the time. Quantum mechanics, unlike classical physics, deals with the behavior of particles at a very small scale, atoms and subatomic particles. These particles, such as electrons, do not behave like the macroscopic objects we encounter in everyday life. Instead, their behavior is governed by probabilities rather than certainties. This departure from classical mechanics is one of the reasons quantum mechanics is so difficult to conceptualize. It suggests that particles can exist in multiple states at once, and their exact position or momentum cannot be determined until measured. The idea that particles are probabilistic rather than deterministic was already present in the work of other physicists like Niels Bohr and Albert Einstein, but Heisenberg's uncertainty principle provided a concrete mathematical framework to support it. At the core of the uncertainty principle is the relationship between position and momentum. Position refers to where a particle is located in space, and momentum is the product of its mass and velocity. In classical physics, it was assumed that if you knew a particle's position and momentum, you could predict its future path. However, Heisenberg showed that the more accurately you measure one of these properties, the less precisely you can measure the other. This is because the act of measuring one property disturbs the other, which is a direct consequence of the wave-particle duality of quantum particles. To understand this better, imagine a situation where you are trying to measure the position of an electron. In classical physics, we could shine light on the electron and measure how it interacts with the light to determine its position. However, in quantum mechanics, the act of observing the electron actually affects its momentum. The more precisely you try to measure the position, the more uncertain the momentum becomes. This is because the light used to measure the position imparts energy to the electron, causing it to move. Conversely, if you focus on measuring the momentum of the particle, the position becomes uncertain because the act of measuring momentum interferes with the particle's location. The mathematical expression of this principle, delta x delta p greater than or equal to as 2, encapsulates this relationship. Here, delta x is the uncertainty in position, delta p is the uncertainty in momentum, and L, h bar, is the reduced Planck constant. This equation shows that the product of the uncertainties in position and momentum is always greater than or equal to a constant value. The smaller the uncertainty in one property, the larger the uncertainty in the other. One of the most profound implications of Heisenberg's uncertainty principle is that it fundamentally challenges our classical understanding of the universe. In classical mechanics, the universe was thought to be deterministic, meaning that if you knew the current state of a system, position, velocity, etc., you could predict its future behavior with absolute certainty. Heisenberg's principle, however, introduces a level of unpredictability at the quantum scale. It tells us that, at least at this scale, the universe is not deterministic. Instead, it is probabilistic, governed by uncertainty and chance. This realization had a profound impact on the philosophy of science, leading to debates about the nature of reality itself. Moreover, Heisenberg's uncertainty principle also challenges the concept of objective reality. In classical physics, it was assumed that the properties of an object existed independently of the observer. That is, the position and momentum of a particle were thought to be definite whether or not anyone was measuring them. In quantum mechanics, however, The act of measurement plays a crucial role in determining the state of a system. The properties of a particle, like its position and momentum, are not definite until they are observed. Before observation, particles exist in a superposition of states, meaning they can occupy multiple positions or momenta at once. Only when we measure these properties do they collapse into one specific value. This idea, often associated with the famous thought experiment of Schrödinger's cat, raises important questions about the role of the observer in shaping reality. Heisenberg's principle also led to significant advancements in quantum mechanics and was essential for the development of later theories in physics. It laid the groundwork for the study of quantum entanglement, where particles become correlated in ways that defy classical physics. In entangled systems, the state of one particle is instantaneously connected to the state of another, regardless of the distance between them. This phenomenon has been experimentally verified, further confirming the strange and non-intuitive nature of quantum mechanics. The uncertainty principle also helped to establish the concept of quantum fields, which describe the fundamental forces of nature. In these fields, particles are not fixed objects but are instead excitations or ripples in the underlying field. The principle that particles cannot have both precise position and momentum is closely related to the idea that quantum fields are inherently uncertain and fluctuate at the smallest scales. These fluctuations are responsible for the creation of particles and are a fundamental feature of the quantum vacuum. At its core, Heisenberg's uncertainty principle reshapes our understanding of reality by showing that uncertainty is not just a limitation of our measurements, but a fundamental feature of the universe. It tells us that at the quantum level, the universe is inherently probabilistic, and there are limits to how much we can know about the nature of reality. This realization has profound implications for our understanding of the physical world and has led to the development of technologies such as quantum computing and quantum cryptography, which exploit the strange properties of quantum systems for practical application. In conclusion, Heisenberg's uncertainty principle was a groundbreaking discovery that shook the very foundations of physics and our understanding of the universe. It introduced a new way of thinking about particles, measurement, and the nature of reality itself. The uncertainty principle is not just a scientific concept, it is a philosophical challenge that continues to inspire debates about the limits of human knowledge and the true nature of the universe. Despite its counterintuitive nature, it has had a lasting impact on both theoretical and applied physics, and its legacy continues to shape the way we think about the quantum world. Heisenberg's uncertainty principle shook the foundations of physics and led to a dramatic shift in how we understand the universe, particularly at the quantum level. To fully grasp the profound impact of this principle, it is important to explore not only its mathematical framework and scientific implications, but also how it reshaped our philosophical and metaphysical views of the physical world. The uncertainty principle, formulated by Werner Heisenberg in 1927, asserts that certain pairs of physical properties of a particle, such as its position and momentum, cannot be precisely measured at the same time. This is a direct challenge to the assumptions of classical physics, which was based on the belief that the universe is deterministic. Classical mechanics, built by figures like Isaac Newton, suggested that if you knew the exact position and velocity of every particle in the universe, you could predict its future behavior with absolute precision. In this framework, the universe operated like a giant clock, where every event could be traced back to a previous cause. Heisenberg's uncertainty principle introduces a level of indeterminacy that defies this classical notion of the world. It is important to recognize that Heisenberg did not propose that the uncertainty is a result of human limitations in measurement or the imperfections of instruments. Instead, it is a fundamental characteristic of nature itself. In quantum mechanics, particles are not viewed as discrete objects with well-defined properties at all times. Rather, they exist in a state of probability until they are observed. The uncertainty principle is a reflection of this probabilistic nature of quantum particles. To understand the principle mathematically, we consider the relationship between position and momentum. Position refers to where a particle is located, and momentum is the product of the particle's mass and velocity. Heisenberg showed that the more precisely we know a particle's position, delta, the less precisely we can know its momentum, delta, and vice versa. This relationship is encapsulated in the inequality deltax, delta greater than or equal to O, where O is the reduced Planck constant. This equation shows that the uncertainties in position and momentum must always multiply to be greater than or equal to a constant value. Thus, if we reduce the uncertainty in one of these measurements, the uncertainty in the other must increase. The significance of Heisenberg's uncertainty principle lies not just in its mathematics, but in the profound conceptual shift it brought to the study of the physical world. For centuries, physics had operated on the assumption that with enough data, we could measure and predict the state of any system. The uncertainty principle directly contradicted this, asserting that there are limits to how much we can know about a system at a quantum level. This does not mean that the universe is inherently chaotic or random in an unstructured way, but rather that uncertainty is built into the fabric of reality itself. At the quantum level, the precise state of a system is unknowable in a classical sense. Moreover, the uncertainty principle is intimately tied to the concept of wave-particle duality, a cornerstone of quantum mechanics. In quantum theory, particles, such as electrons, are described not as tiny billiard balls but as wave-like entities with probabilistic distributions. This wave-like behavior leads to the idea that particles do not have a definite position or momentum until they are observed. The act of observation itself alters the system, collapsing the wave function, which describes the range of possible states of a particle into one specific state. This idea was famously illustrated in Schrödinger's cat thought experiment, where a cat inside a box is both alive and dead until observed, symbolizing the strange superposition of states that quantum particles can occupy. The relationship between uncertainty and measurement in quantum mechanics further complicates our classical understanding of reality. In the quantum world, particles are not only affected by the observer's presence, but the very act of observation becomes an integral part of the physical process. This challenges the classical notion of an objective reality that exists independently of human observation. The idea that reality is, in some sense, observer-dependent forces a rethinking of metaphysical questions about the nature of existence. Does the universe exist in a definite state regardless of our perception, or is it fundamentally shaped by the act of observation? These questions, which were once considered philosophical or speculative, became central concerns in the philosophy of science after Heisenberg's work. The implications of the uncertainty principle go beyond just fundamental physics. It has had practical consequences in several fields of science and technology. One of the most important applications of the uncertainty principle is in the development of technologies that exploit quantum properties, such as quantum computing and quantum cryptography. Quantum computers, which are still in their early stages of development, have the potential to revolutionize information processing by using quantum bits or qubits. Unlike classical bits, which represent either 0 or 1, qubits can exist in superposition, representing both 0 and 1 simultaneously. This ability to exist in multiple states simultaneously is a direct consequence of the probabilistic nature of quantum particles. The uncertainty principle is central to understanding the limits and capabilities of such technologies. Quantum cryptography, on the other hand, uses the principles of quantum mechanics to secure communication. It relies on the idea that any attempt to eavesdrop on a quantum system will disturb its state, making interception detectable. This is a direct consequence of the uncertainty principle, which implies that the act of measuring a quantum system will always introduce uncertainty, allowing the sender and receiver to detect any tampering with their communication. The philosophical ramifications of Heisenberg's uncertainty principle are immense. It challenges the very concept of determinism, which had been the foundation of classical physics. Determinism is the idea that every event or state is determined by prior events, and if we had perfect knowledge of the current state of the universe, we could predict the future with absolute certainty. Heisenberg's principle suggests that such an idea is not possible at the quantum level. This idea has led to the development of interpretations of quantum mechanics, such as the Copenhagen interpretation, which accepts the indeterminacy of quantum systems as a fundamental feature of the universe. Other interpretations, like the many worlds interpretation, offer different solutions to the problem of measurement and observation in quantum mechanics. The uncertainty principle also poses a challenge to our traditional notions of causality and free will. If the future is not entirely determined by the present, as the uncertainty principle suggests, what does this mean for the concept of free will? Can human decisions be truly free if the future is shaped by probabilistic events? These questions have become central to debates in both science and philosophy, as Heisenberg's principle opened up a new era of inquiry into the nature of knowledge, reality, and the universe itself. Despite its initially controversial nature, Heisenberg's uncertainty principle has become one of the most fundamental and accepted aspects of quantum mechanics. It has forced scientists, philosophers, and thinkers across the world to reconsider the nature of reality, the role of the observer, and the limits of human knowledge. It reshaped the way we think about the physical world and continues to be a source of inspiration, intrigue, and debate in both science and philosophy. In conclusion, Heisenberg's uncertainty principle was not merely a scientific breakthrough. It was a paradigm shift that reshaped our entire understanding of the universe. By revealing the inherent uncertainty at the quantum level, Heisenberg challenged our classical worldview and introduced a probabilistic, observer-dependent reality. The uncertainty principle has had far-reaching implications, from its philosophical consequences to its practical applications in modern technology. It is a testament to the power of scientific inquiry to challenge our deepest assumption about the nature of existence, and has left an indelible mark on the history of science. Heisenberg's uncertainty principle, as discussed in the first keynote, shattered the classical view of the universe and presented an entirely new framework for understanding the microcosmic world of quantum mechanics. Its implications extended beyond just a theoretical concept. It became a central principle that would forever change the way scientists approached the study of nature. But what were the broader consequences of this groundbreaking theory? To answer this, we turn to the second keynote, which explores the impact of Heisenberg's uncertainty principle on the interpretation of quantum mechanics and its philosophical implications on our understanding of reality itself. The advent of the uncertainty principle marked a decisive moment in the history of physics. While quantum mechanics was not a completely new field at the time Einstein, Planck, and Bohr had already made significant strides, it was Heisenberg's work that provided a deeper insight into the very foundation of quantum mechanics, influencing both the science and philosophy of the 20th century. To understand its profound impact, we must first explore the concept of wave-particle duality and how it intertwined with Heisenberg's principle. Wave-particle duality is the idea that particles, like electrons, can exhibit both particle-like and wave-like behavior depending on how they are observed. This duality was introduced by Louis de Broglie, who proposed that particles could behave like waves, a concept that seemed utterly incompatible with classical physics at the time. The dual nature of particles meant that the properties of particles, such as their position or momentum, could no longer be described in terms of deterministic classical variables. Instead, quantum objects existed in states of probability, which, when measured, would collapse into a single, observable value. This idea was radical and deeply unsettling for many physicists because it contradicted the Newtonian, mechanistic view of a universe governed by precise laws of motion. Heisenberg's uncertainty principle took wave-particle duality a step further by making the uncertainty of certain measurements a fundamental part of the quantum world. Heisenberg's groundbreaking realization that it was impossible to measure both the position and momentum of a particle with absolute precision revealed that the act of measurement itself has intrinsic consequences on the system being measured. This was a stark contrast to classical physics, where the observer was considered a passive entity whose only role was to record the pre-existing state of the universe. In the quantum world, however, the observer's intervention altered the system, a concept that was deeply revolutionary. This shift in how we view measurement in quantum mechanics was radical. In classical physics, measurements were thought to be objective and independent of the observer. You could, in theory, measure an object's position, velocity, and other properties without affecting the object itself. In quantum mechanics, however, measurement was no longer a passive activity. The very act of observation influenced the system. For example, if you measure the position of an electron with great precision, you simultaneously introduce uncertainty into its momentum. The more accurately you know one of these properties, the less certain you can be about the other. This new way of understanding measurement had profound implications for how scientists approached not just quantum mechanics but the nature of science and reality itself. Moreover, this new understanding led to one of the most significant debates in the philosophy of science: the role of the observer in determining the reality of a system. The famous Copenhagen interpretation, developed by Niels Bohr and others, embraced the uncertainty principle and the probabilistic nature of quantum mechanics. According to this interpretation, the wave function of a quantum system represents the probabilities of the various possible states of the system, and only when a measurement is made does the wave function collapse into one of those states. Until the act of observation, the system exists in a superposition of all possible states. This view suggests that reality, at least at the quantum level, is not something that exists independently of our observation. Instead, it is shaped by the act of measurement itself. This idea was deeply controversial, as it suggested that the universe could not be fully understood without taking the observer into account. The uncertainty principle also led to significant debates among some of the most prominent physicists of the 20th century. Albert Einstein, famously uncomfortable with the idea of a universe governed by probabilities, famously quipped, "God does not play dice with the universe." Einstein's discomfort with the Copenhagen interpretation and the role of the observer led him to propose that quantum mechanics, in its current form, was incomplete. Einstein believed that there must be hidden variables, undiscovered factors that could explain the probabilistic nature of quantum mechanics in a deterministic way. While Einstein's views were not widely accepted, his arguments prompted further inquiry into the interpretation of quantum mechanics and the limits of our knowledge. One of the most important consequences of the uncertainty principle was that it forced scientists to reconsider the very notion of determinism. In classical physics, determinism was the bedrock of our understanding of the universe. If we knew the position and momentum of every particle, we could, in theory, predict the future with absolute certainty. But Heisenberg's uncertainty principle, and quantum mechanics as a whole, suggested that this was impossible. In the quantum world, uncertainty and indeterminacy were not just byproducts of our measurement limitations, but intrinsic properties of nature. This opened the door to a new way of thinking about the universe, one that embraced probability, uncertainty, and the fundamental limits of human knowledge. The uncertainty principle's challenge to determinism also raised important questions about free will. If the universe at the quantum level is governed by uncertainty, what does this mean for the future of macroscopic objects, including human beings? Are we simply following a predetermined course laid out by probabilistic quantum events? Or do we have the ability to make independent choices? These philosophical questions remain at the heart of discussions about quantum mechanics and its relationship to the nature of consciousness and reality. Heisenberg's uncertainty principle also sparked a new era of scientific innovation. It directly influenced the development of quantum technology, a field that continues to evolve. Quantum computing, which has the potential to revolutionize industries by solving complex problems much faster than classical computers, relies on principles of superposition and entanglement, ideas that were made possible by Heisenberg. Insight into the probabilistic nature of quantum systems. Quantum cryptography, which exploits the uncertainty in quantum systems to secure communication, is another practical application that has emerged as a result of the uncertainty principle. These technologies are still in their infancy, but their potential to reshape industries and society is enormous. Another area where Heisenberg's uncertainty principle has had a lasting impact is in the field of quantum field theory, which describes the fundamental forces of nature. Quantum fields, unlike classical fields, are subject to fluctuations and uncertainty at their core. These fluctuations are responsible for the creation of particles and the interactions between them. The uncertainty principle is central to the understanding of these fields, and it helps to explain phenomena such as the Casimir effect, where vacuum fluctuations give rise to measurable forces between objects. In this sense, the uncertainty principle is not just a theoretical construct. It is a key ingredient in the very nature of the universe. The far-reaching implications of the uncertainty principle cannot be overstated. It fundamentally changed our understanding of the physical world, forcing us to abandon the classical, deterministic view and embrace a probabilistic and observer-dependent reality. The principle's influence extended far beyond physics into philosophy, technology, and even our everyday conception of the universe. While much of quantum mechanics remains mysterious, Heisenberg's uncertainty principle remains one of the most profound and transformative concepts in the history of science. As we look forward to the future, it is clear that the uncertainty principle will continue to influence not just the development of new technologies, but our understanding of reality itself. From quantum computing to the philosophical implications of observation, Heisenberg's legacy endures as a cornerstone of modern physics. The principle forces us to confront the limits of knowledge, the role of the observer, and the fundamentally unpredictable nature of the universe. It reminds us that at the smallest scales, the universe operates in ways that are beyond our comprehension, and that uncertainty is not just a limitation of measurement, but a fundamental feature of the cosmos itself. The impact of Heisenberg's uncertainty principle goes far beyond just the realm of physics. It has profoundly influenced philosophy, technology, and even the way we perceive the universe. In this part, we'll delve into the broader consequences of the uncertainty principle, not only in its scientific applications, but also in how it reshaped our worldview and philosophical understanding of the cosmos. First, let us consider the reaction of the scientific community to Heisenberg's groundbreaking discovery. While Heisenberg's principle was initially met with surprise and skepticism, it gradually became a cornerstone of quantum mechanics. Unlike classical mechanics, which was based on deterministic laws of motion, quantum mechanics operates on probabilistic principles, which Heisenberg's uncertainty principle encapsulates. This shift in perspective was not easy to accept. For centuries, scientists, following the tradition of Newton and Einstein, had believed that the universe operated like a giant clockwork mechanism where all future events could be predicted from a complete knowledge of the present. However, Heisenberg's assertion that uncertainty is inherent in nature itself posed a serious challenge to this deterministic view. The uncertainty principle's greatest implication was its suggestion that the universe, at least at the quantum level, is not governed by absolute precision. In classical physics, precision in measurement meant that you could make predictions with certainty. For example, if you knew the position and velocity of a ball, you could predict where it would go next with complete accuracy. In quantum mechanics, however, such precision is impossible. The more precisely you measure one property of a particle, the less precisely you can know the other. This was a revolutionary concept because it meant that at the fundamental level, nature itself was indeterminate. This indeterminacy does not just apply to position and momentum. Heisenberg's uncertainty principle is a reflection of the wave-particle duality that lies at the heart of quantum mechanics. The wave-particle duality suggests that particles, such as electrons, do not have definite properties until they are measured. Prior to observation, they exist in a superposition of all possible states. For instance, an electron does not have a definite position in space until it is measured. Instead, it exists as a probability wave, with different positions being possible, each with a certain probability. When you measure the electron's position, you force it to collapse into a definite state. But this collapse is not deterministic, it is probabilistic. And Heisenberg's principle governs the limits of this process. The idea that reality is not fully determined until observed has profound implications for our philosophical understanding of the universe. Before Heisenberg, many scientists and philosophers believed that reality was objective and independent of the observer. The idea was that the world existed with definite properties whether or not anyone was there to observe it. However, Heisenberg's uncertainty principle suggests that the act of observation plays a fundamental role in shaping reality itself. The observer, in quantum mechanics, is not just a passive participant who records the state of the universe. Instead, the observer actively influences the system being observed. This realization led to debates between some of the greatest minds of the 20th century. Albert Einstein, perhaps the most famous critic of quantum mechanics, could not accept the probabilistic nature of reality suggested by Heisenberg. Einstein's views were rooted in the belief that the universe must operate in a deterministic manner. He famously expressed his discomfort with the idea of a probabilistic universe by saying, "God does not play dice with the universe." Einstein believed that quantum mechanics while successful in explaining the behavior of particles, was incomplete. He proposed that there must be hidden variables, undiscovered factors that could restore determinism to the quantum world. Despite Einstein's reservations, Heisenberg's uncertainty principle was supported by many other prominent physicists, including Niels Bohr. The Copenhagen interpretation of quantum mechanics, developed by Bohr and others, accepted the inherent uncertainty in nature as a fundamental feature of the quantum world. According to this interpretation, particles do not have definite positions or momenta until they are measured. Before measurement, they exist in a superposition of possible states, each with a certain probability. This view of reality, one in which the act of observation plays a critical role in determining the state of the system, was radical and difficult for many to accept. But as experiments continued to confirm the predictions of quantum mechanics, the uncertainty principle became firmly entrenched as a core aspect of the theory. The philosophical implications of the uncertainty principle went beyond just the nature of observation. It also led to important questions about the nature of causality and free will. In classical physics, causality was a cornerstone of the scientific worldview. Every event was considered to have a cause, and in principle, if you knew all the conditions of a system, you could predict its future with certainty. Heisenberg's uncertainty principle, however, suggested that not everything could be determined by prior causes. In the quantum world, outcomes are governed by probabilities, and the future of a system cannot be predicted with absolute certainty. This raised important questions about the nature of free will. If the universe is governed by probabilistic events where uncertainty is fundamental, does this mean that our choices are predetermined? Or is there room for free will in this framework? Furthermore, Heisenberg's principle had a significant impact on the development of quantum technologies. One of the most important practical applications of the uncertainty principle has been in the field of quantum cryptography. Quantum cryptography takes advantage of the fact that measurement at the quantum level disturbs the system. In quantum key distribution, for example, any attempt to eavesdrop on the communication would introduce detectable disturbances in the system. This makes quantum cryptography a potentially unbreakable form of encryption. The uncertainty principle, which highlights the inherent disturbance caused by observation, is central to the security of quantum cryptography systems. Another area where Heisenberg's principle has had a profound impact is quantum computing. In classical computing, information is processed using binary bits, which can represent either 0 or 1. Quantum computers, on the other hand, use quantum bits or qubits, which can exist in a superposition of states, representing both 0 and 1 simultaneously. This ability to exist in multiple states at once is a direct consequence of the uncertainty principle. Quantum computers could, in theory, perform certain calculations much more efficiently than classical computers, and they hold the potential to revolutionize fields such as cryptography, artificial intelligence, and complex simulation. Heisenberg's uncertainty principle also helped shape the development of quantum field theory, QFT, which describes the fundamental forces of nature. In QFT, particles are not viewed as individual objects, but rather as excitations or ripples in underlying fields. The uncertainty principle plays a key role in understanding the behavior of these fields. It suggests that quantum fields are inherently uncertain and fluctuate at the smallest scales. These fluctuations, which are a direct consequence of Heisenberg's principle, are responsible for the creation of particles and interactions between them. The uncertainty principle, therefore, is central to understanding the dynamics of quantum fields and the interactions that govern the universe at the smallest scales. The far-reaching consequences of Heisenberg's uncertainty principle continue to influence not just quantum mechanics, but the very way we think about the nature of reality itself. It challenges our classical notions of determinism, objectivity, and the independence of the observer. It forces us to accept that, at the quantum level, uncertainty is not merely a limitation of our knowledge, but a fundamental feature of nature. This realization has had profound implications, not only for science but for philosophy, ethics, and even our everyday understanding of the universe. While Heisenberg's uncertainty principle remains one of the most puzzling and counterintuitive aspects of quantum mechanics, it is also one of the most powerful and transformative ideas in the history of science. As quantum mechanics continues to evolve, the legacy of Heisenberg's uncertainty principle endures. It continues to shape not only the way we study the quantum world, but also the technologies we build and the philosophical questions we ask. It is a constant reminder that the universe, at its most fundamental level, is not as predictable, deterministic as we once thought, and that uncertainty is woven into the very fabric of reality. Heisenberg's uncertainty principle is a cornerstone of quantum mechanics that forever changed the way we view the universe. Introduced by Werner Heisenberg in 1927, it fundamentally altered our understanding of the microscopic world. The uncertainty principle not only reshaped the scientific community's view of reality, but also had profound philosophical and technological consequences. In this part, we will explore the third keynote, which delves deeper into the significance of the uncertainty principle, its connection to wave-particle duality, its role in quantum mechanics, and the broader implications for understanding the nature of reality itself. The uncertainty principle emerged during a period of rapid advancements in physics when the classical deterministic worldview was being challenged by new, counterintuitive theories in quantum mechanics. Classical physics, particularly the work of Isaac Newton, had long been based on the idea that the universe operates in a predictable, deterministic manner. If we know the current state of a system, such as the position and velocity of a particle, we should, in theory, be able to predict its future behavior with complete certainty. This was the heart of Newtonian mechanics. However, the advent of quantum mechanics brought to light a different, and far more complicated, picture of the physical world. Heisenberg's uncertainty principle contradicted the classical notion of determinism. It states that we cannot measure both the position and momentum of a particle with absolute precision at the same time. The more accurately we know one of these properties, the less precisely we can know the other. This was not due to limitations in measurement devices or human error, but instead a fundamental feature of the universe at the quantum level. The principle introduced the idea that uncertainty is inherent in nature, and this was a radical departure from classical thinking. The principle is often described mathematically as deltax deltap greater than or equal to as 2, where deltax is the uncertainty in position, deltap is the uncertainty in momentum, and L, h bar, is the reduced Planck constant. This equation reveals the intrinsic limitations of measurement in the quantum world. The principle is often misunderstood, as it does not imply that we are simply incapable of making precise measurements, but that the act of measurement itself disturbs the system. This disturbance introduces uncertainty that is not avoidable, no matter how sophisticated our tools become. At its core, Heisenberg's uncertainty principle highlights a paradox. The more precisely we measure the position of a particle, the less precisely we can know its momentum, and vice versa. This is because in quantum mechanics, particles are not localized objects that can be pinpointed with perfect accuracy. Instead, they exhibit wave-like behavior, which leads to a probabilistic distribution of where they might be found. This wave-particle duality, where particles exhibit both wave-like and particle-like properties, underpins the uncertainty principle. The wave-particle duality was proposed by Louis de Broglie, who suggested that all particles, including electrons, have wave-like properties. This was an extension of Einstein's work on the photoelectric effect, where light was shown to behave as both a wave and a particle. In the quantum world, particles like electrons are described not as fixed points in space, but as probability waves that spread out over a range of locations. The position of an electron, for example, is not a definite point, but a probability distribution of where the electron might be found. The act of measuring its position causes the probability wave to collapse, revealing a definite location. This wave-like nature of particles is at the heart of the uncertainty principle. When we measure the position of a particle, we are forcing its wave-like nature to collapse into a specific point. However, the wave nature of particles also means that their momentum is spread out over a range of possible values. The more precisely we measure the position of the particle, the more the wave function spreads out in momentum space, leading to greater uncertainty in momentum. This is a fundamental feature of quantum mechanics. The very nature of particles at the quantum scale is inherently probabilistic. The uncertainty principle is a direct consequence of the wave-particle duality and the mathematical framework of quantum mechanics. In classical mechanics, particles were thought to have definite properties, and these properties could be measured with arbitrary precision. In quantum mechanics, however, The wave-like nature of particles prevents this. Particles do not have definite positions or momenta until they are measured, and the act of measuring them disturbs their state, making it impossible to know both their position and momentum precisely. This realization led to a dramatic shift in our understanding of the universe. Prior to Heisenberg's work, scientists believed that the universe could be fully understood and predicted if we knew enough about the current state of a system. The uncertainty principle shattered this belief, suggesting that there are fundamental limits to what we can know about the physical world. The implications of this principle are far-reaching, not just for physics, but for our understanding of reality itself. One of the most important implications of the uncertainty principle is its impact on the concept of causality. In classical physics, causality is a cornerstone of our understanding of the universe. Every effect has a cause, and if we know the present state of a system, we can predict its future with complete certainty. However, in the quantum world, the uncertainty principle introduced a level of indeterminacy that challenges this deterministic view. Quantum mechanics operates on probabilistic principles, meaning that we can never know the exact future state of a system. Instead, we can only predict the probabilities of different outcomes. This fundamentally changes our view of the universe. The future is not a predetermined path that we can simply uncover through measurement and calculation, but a realm of possibilities governed by probabilities. The uncertainty principle also has profound implications for the nature of reality itself. It challenges the classical view that the universe exists independently of the observer. In classical physics, it was assumed that objects and particles had definite properties that exist whether or not we observe them. However, in quantum mechanics, the act of observation plays a critical role in determining the properties of a system. This idea is most famously illustrated in Schrodinger's cat thought experiment, where a cat is both alive and dead until observed, representing the superposition of states that quantum particles can occupy. In quantum mechanics, particles exist in a superposition of all possible states until they are measured. It is only through the act of measurement that a particle's wave function collapses into a definite state. This observer-dependent nature of reality leads to one of the most profound philosophical questions raised by quantum mechanics. Does the universe exist independently of our observation, or is reality itself shaped by our perception? The uncertainty principle suggests that the act of measurement is not just a passive recording of information, but an active participant in determining the state of a system. This challenges our classical view of a deterministic, observer-independent reality and introduces a new way of thinking about the universe, a universe in which uncertainty and probability play a fundamental role. The uncertainty principle also has important consequences for the development of new technologies. One of the most significant applications of Heisenberg's work has been in the field of quantum computing. Quantum computers, unlike classical computers, use quantum bits or qubits, which can exist in multiple states simultaneously. This ability to exist in superposition, where a qubit can represent both 0 and 1 at the same time, is a direct consequence of the probabilistic nature of quantum mechanics. Quantum computers harness the power of quantum uncertainty to perform certain calculations exponentially faster than classical computers. This has the potential to revolutionize fields such as cryptography, artificial intelligence, and complex simulation. Another key application of the uncertainty principle is quantum cryptography. Quantum cryptography takes advantage of the fact that measurement at the quantum level disturbs the system. In quantum key distribution, for example, any attempt to eavesdrop on the communication would introduce detectable disturbances in the system. This makes quantum cryptography a potential unbreakable form of encryption, as any attempt to intercept the communication would be immediately noticed. In conclusion, Heisenberg's uncertainty principle is not just a theoretical concept, but a profound shift in our understanding of the universe. It highlights the inherent uncertainty at the quantum level and challenges the classical deterministic worldview by showing that the act of observation itself influences the system being measured. The uncertainty principle reshapes our view of reality. It opens up a new understanding of the physical world, where uncertainty, probability, and the role of the observer are central. The principle's influence extends far beyond physics, impacting philosophy, technology, and even our everyday perception of the universe. Through its application in fields such as quantum computing and quantum cryptography, Heisenberg's uncertainty principle continues to shape the future of science and technology. Heisenberg's uncertainty principle fundamentally shifted our understanding of the universe, particularly within the realms of quantum mechanics and our philosophical grasp of reality. This principle not only challenged the prevailing Newtonian worldview of deterministic laws but also ignited a revolution that reshaped the core ideas of physics, philosophy, and technology. In this part, we will explore the broader consequences and implications of Heisenberg's uncertainty principle, its connection with wave-particle duality, and how it revolutionized the way we understand both the microscopic world and the universe at large. At the heart of the uncertainty principle is the idea that there are fundamental limitations to how precisely we can measure certain pairs of properties of a quantum particle, such as its position and momentum, at the same time. This principle arose at a time when classical mechanics was thought to provide an all-encompassing framework for understanding the physical world. In classical physics, the belief was that with enough data, one could predict the future trajectory of any particle if its initial conditions were known. However, Heisenberg's principle threw this certainty into disarray, asserting that the act of measuring one property inherently disturbs the other, rendering it impossible to determine both with absolute precision. This concept directly opposed the deterministic worldview of classical physics, where everything in the universe was governed by predictable laws. In quantum mechanics, particles do not behave like classical objects with well-defined positions and velocities. Instead, they are described by wave functions that represent probabilities, with the position and momentum of particles being inherently uncertain until observed. The measurement of these properties collapses the particle's wave function into a definitive state. In essence, quantum particles do not exist in definite states until we measure them, challenging the classical notion of an objective reality. This was the beginning of a paradigm shift, one where uncertainty and indeterminacy were not seen as imperfections in our knowledge, but as intrinsic to the fabric of nature. The wave-particle duality, another cornerstone of quantum mechanics, is crucial to understanding the uncertainty principle. The idea that particles, like electrons, exhibit both particle-like and wave-like properties was proposed by Louis de Broglie and was later confirmed in experiments. This duality suggested that particles do not have definite properties until observed. Instead, they exist as probability waves, meaning their position, momentum, and other properties are spread out over a range of values until they are measured. Heisenberg's uncertainty principle arose from this idea: the more accurately we attempt to measure the position of a particle, the less accurately we can know its momentum, and vice versa. This arises from the fact that at the quantum scale, particles do not have a single, localized position. Instead, they are spread out as a wave with a range of possible positions and momenta. Measurement then forces this wave to collapse into one definite value. This idea appends the classical view of reality. In classical physics, objects had specific locations and velocities that existed independent of any observer. The position and momentum of an object could be measured with perfect precision without altering its state. However, the uncertainty principle suggests that, at the quantum level, this is no longer true. The process of measurement itself plays an active role in determining the state of the system. When you measure the position of a particle, you influence its momentum, and vice versa. This leads to an inherent disturbance in the system, which is unavoidable. The universe, at the quantum level, is not just an objective reality that exists independently of observation. Instead, the act of observing the system alters it in a fundamental way. This realization has profound implications, not just for physics, but for our understanding of the nature of reality. The philosophical ramifications of the uncertainty principle are far-reaching. For centuries, the prevailing worldview was based on the idea that the universe operated in a deterministic, predictable manner. Classical physics, with its focus on precision and measurement, was rooted in the belief that the universe had an objective reality that could be fully understood and predicted if enough data was available. The uncertainty principle, however, introduces an element of indeterminacy into this picture. If the universe at the quantum level is governed by uncertainty, then it is no longer fully deterministic. This shifts the philosophical debate from a deterministic to a probabilistic model of reality. Moreover, the uncertainty principle challenges the classical idea of the observer as a passive participant in the scientific process. In classical physics, the observer's role was seen as that of a neutral recorder of the state of the system. In quantum mechanics, however, the observer plays an active role in shaping the state of the system. This has led to significant philosophical debates about the nature of reality. If the act of measurement influences the system, does that mean that reality is observer-dependent? Is the universe in a state of potentiality until it is observed, collapsing into a definite state only when measured? These questions have prompted new interpretations of quantum mechanics, such as the Copenhagen interpretation and the many-world interpretation, each attempting to reconcile the observer's role with the strange, indeterminate nature of the quantum world. Heisenberg's uncertainty principle also posed challenges to the classical notion of causality. In classical mechanics, every event or state of the system was assumed to have a cause, and if we knew the current state of a system, we could predict its future with absolute certainty. However, the probabilistic nature of quantum mechanics, as encapsulated by the uncertainty principle, means that we cannot predict the exact future state of a system. Instead, we can only determine the probabilities of different outcomes. This introduces a level of randomness into the behavior of particles, which contradicts the classical idea of a fully determined, predictable universe. The future is no longer a fixed trajectory, but a range of possibilities, each with its own probability. The implications of the uncertainty principle also extended beyond philosophical debates to the development of technology. Quantum mechanics and its probabilistic principles have given rise to revolutionary technologies such as quantum computing and quantum cryptography, which rely on the strange properties of quantum particles. Quantum computers, for example, use qubits, which can exist in multiple states at once. This ability to exist in superposition, a direct consequence of quantum uncertainty, allows quantum computers to perform certain calculations much more efficiently than classical computers. This has the potential to revolutionize industries such as cryptography, artificial intelligence, and complex simulation. Quantum cryptography, another direct application of the uncertainty principle, exploits the fact that any attempt to observe a quantum system will disturb it. This makes quantum key distribution, QKD, a potentially unbreakable form of encryption. In QKD, any attempt to intercept the communication introduces detectable changes in the quantum system, allowing the sender and receiver to detect eavesdropping. This technology is already being explored for securing communications in fields such as government, finance, and defense. Another important application of the uncertainty principle is in the field of quantum field theory, QFT, which describes the fundamental forces of nature. Quantum fields are not seen as static entities but as fluctuating entities that exist in a constant state of uncertainty. The uncertainty principle is crucial to understanding how particles and fields interact. It suggests that quantum fields are subject to fluctuations and uncertainty, and these fluctuations are responsible for the creation of particles and the interactions between them. The uncertainty principle is central to the study of these fluctuations and their impact on the fabric of the universe. In conclusion, Heisenberg's uncertainty principle is more than just a scientific discovery. It is a paradigm-shifting concept that fundamentally changed our understanding of the universe. It forced scientists to abandon the classical, deterministic view of the world and embrace a probabilistic, uncertain view of reality. The uncertainty principle not only had profound implications for physics, but also influenced our philosophical understanding of the nature of reality, the role of the observer, and the limits of human knowledge. It opened the door to new technologies, such as quantum computing and quantum cryptography, that are already reshaping industries. Through its far-reaching consequences, the uncertainty principle continues to be a defining feature of the modern scientific worldview, one that recognizes uncertainty and indeterminacy as essential features of the universe. Heisenberg's uncertainty principle revolutionized our understanding of the microscopic world, and its implications stretched far beyond the realm of physics. The principle asserts that certain pairs of properties of a particle, such as its position and momentum, cannot be measured simultaneously with perfect accuracy. This concept was a profound departure from classical physics, which adhered to the belief that all physical properties could be known precisely if measured correctly. In quantum mechanics, however, Heisenberg demonstrated that measurement itself introduced an inherent uncertainty, disrupting the very fabric of classical certainty. The impact of this principle extended into the broader framework of quantum mechanics. Quantum mechanics, with its probabilistic nature, suggested that the behavior of particles cannot be predicted with absolute certainty. Rather than operating in a deterministic way like classical systems, particles exist in a superposition of states, and their properties are defined only when measured. The uncertainty principle provides a mathematical representation of this probabilistic world, showing that as we attempt to measure one property of a particle with precision, the other property becomes more uncertain. This disturbance is not a result of human error or faulty equipment. It is a fundamental characteristic of nature. As a consequence, the idea of a purely objective reality, independent of observation, began to dissolve in the face of quantum mechanics. The principle also directly ties to the wave-particle duality of quantum objects, a cornerstone of quantum theory. In classical mechanics, particles were viewed as distinct objects with well-defined properties. However, in quantum mechanics, particles like electrons are described as waves, and these waves represent a range of potential positions and momenta. When we attempt to measure a particle's position, its wave-like nature collapses, and a single position is revealed. However, this measurement also disrupts the particle's momentum. Similarly, if we measure momentum with great accuracy, the particle's position becomes uncertain. This duality illustrates the interconnectedness of position and momentum and highlights the limitation placed on our ability to simultaneously know both properties in their exact states. The uncertainty principle demonstrates that the particle is not in a well-defined state at all times. Instead, it exists as a wave of probabilities until observed. The philosophical implications of Heisenberg's uncertainty principle were as profound as its scientific consequences. Classical physics held that the universe was deterministic, that is, if we knew the initial condition of every particle, we could predict the future of the universe. This idea, championed by thinkers like Newton, reinforced the belief in an objective reality that existed independent of human perception. However, the uncertainty principle challenged this deterministic view by introducing the idea that at the quantum level the universe operates probabilistically. Instead of exact predictions, we are given probabilities, highlighting the inherent uncertainty and indeterminacy of nature. This realization sparked debates among scientists and philosophers, including the famous disagreement between Albert Einstein and Niels Bohr. Einstein, resistant to the probabilistic nature of quantum mechanics, famously argued that God does not play dice with the universe, asserting that there must be hidden variables that could restore determinism to quantum theory. While Einstein's objections were not widely accepted, they inspired continued exploration of the interpretation of quantum mechanics and the philosophical implications of the uncertainty principle. Finally, the uncertainty principle laid the groundwork for future innovations in quantum technology. Quantum mechanics, with its inherent uncertainty, led to the development of technologies that harness the strange properties of quantum particles. Quantum computing, for example, relies on the superposition of states, where qubits, quantum bits, exist in multiple states at once. This ability to represent multiple values simultaneously makes quantum computing exponentially faster than classical computing for certain tasks. Similarly, quantum cryptography uses the uncertainty principle to create unbreakable encryption methods. In quantum cryptography, any attempt to intercept or measure the transmission of information will disturb the quantum state, revealing the presence of an eavesdropper. These technologies are just a glimpse into how the uncertainty principle is shaping the future of technology, pushing the boundaries of what is possible by leveraging the strange, uncertain properties of the quantum world. In conclusion, Heisenberg's uncertainty principle was a groundbreaking concept that reshaped the very foundation of physics and philosophy. It demonstrated that the universe at the quantum level operates probabilistically, and that uncertainty is an intrinsic feature of nature. By challenging classical physics, the uncertainty principle introduced a new, probabilistic framework for understanding the physical world. It also spurred the development of revolutionary quantum technologies that are poised to change the world. Ultimately, Heisenberg's discovery forces us to confront the limits of human knowledge and understand that at the smallest scales, uncertainty is not a flaw in our measurement systems but a fundamental characteristic of the universe itself. Heisenberg's uncertainty principle, introduced in 1927, has remained one of the most significant and groundbreaking concepts in quantum mechanics. Its core assertion that certain pairs of properties, such as a particle's position and momentum, cannot be simultaneously measured with perfect accuracy marked a departure from classical physics and introduced a new way of thinking about the microscopic world. The uncertainty principle emerged as a direct challenge to the deterministic worldview upheld by classical mechanics, where the future of a system could be predicted with absolute certainty if its initial conditions were known. Instead, Heisenberg's principle revealed that uncertainty is not just a limitation of measurement but a fundamental feature of the universe. At the heart of the uncertainty principle lies the concept that the more precisely we measure one property of a particle, such as its position, the less precisely we can know its momentum and vice versa. This mathematical relationship is represented by the inequality deltax deltap greater than or equal to as 2, where deltax is the uncertainty in position, deltap is the uncertainty in momentum, and L, h bar, is the reduced Planck constant. Unlike classical physics, where measurement did not disturb the system, quantum mechanics revealed that measurement itself has an inherent effect on the system. The uncertainty is not due to any flaws in our measuring devices or methods, but is an intrinsic property of nature at the quantum level. This was a radical shift in understanding, as it demonstrated that the act of observation interferes with the observed reality. The principle also relates closely to the concept of wave-particle duality, which forms the foundation of quantum mechanics. In classical physics, particles were thought to be discrete objects with well-defined positions and velocities. However, in quantum mechanics, particles like electrons exhibit both wave-like and particle-like properties depending on how they are observed. The duality means that particles, like electrons, do not have a definite position or momentum until they are measured. Instead, they exist in a state of probability, described by a wave function. The uncertainty principle underscores the wave-like nature of particles, as measuring one aspect position or momentum disturbs the other due to the particle's wave-like behavior. This leads to the conclusion that particles do not have distinct, fixed values for both position and momentum simultaneously, challenging classical ideas of determinism and objectivity. Philosophically, the uncertainty principle had a profound impact on how we perceive reality. For centuries, scientists and philosophers had held the belief that the universe operated according to deterministic laws, where knowing the state of a system at one moment in time allowed for the prediction of future states. This classical worldview was anchored in the idea that reality existed independently of observation. However, the uncertainty principle, in conjunction with the broader framework of quantum mechanics, suggested that the act of observation plays a vital role in shaping reality. In quantum mechanics, the properties of particles do not exist in definite states until they are measured. This led to the development of the Copenhagen interpretation of quantum mechanics, which proposed that particles exist in a superposition of states until observed, and only through measurement do they collapse into a single, definite state. This view directly challenges the classical notion of an objective, observer-independent reality, opening up new philosophical debates on the nature of existence and the role of the observer. One of the major consequences of the uncertainty principle is its effect on causality. In classical physics, causality, the idea that every effect has a specific cause, is fundamental. If we know the position and velocity of every particle, we can predict the future with complete certainty. However, quantum mechanics, with its inherent uncertainty, introduces a probabilistic model of reality. Rather than deterministic predictions, quantum mechanics deals with probabilities. The uncertainty principle makes it impossible to predict the exact state of a system with complete certainty. Instead, we can only calculate the likelihood of different outcomes. This fundamentally alters our understanding of causality. At the quantum level, The future is not fully determined by the present, as there is an inherent randomness in the way particles behave. This shift challenges the classical notion that the future is a direct consequence of the present. The uncertainty principle also laid the groundwork for several technological advances that have had a profound impact on modern science and industry. One of the most significant applications of quantum mechanics and the uncertainty principle is in the field of quantum computing. Quantum computers use quantum bits, or qubits, which can exist in multiple states simultaneously due to the principle of superposition. This allows quantum computers to perform calculations at speeds that far exceed those of classical computers for certain tasks. Quantum computing has the potential to revolutionize fields such as cryptography, artificial intelligence, and materials science. Similarly, quantum cryptography, which relies on the uncertainty principle, is being developed as a means of creating secure communication systems. The principle that measurement in quantum systems disturbs the system itself makes it possible to detect eavesdropping attempts, offering a potentially unbreakable form of encryption. In conclusion, Heisenberg's uncertainty principle has had a profound and lasting impact on both science and philosophy. It challenged the deterministic view of the universe and introduced a probabilistic framework for understanding the microscopic world. The principle's implications for wave-particle duality, the nature of observation, and causality revolutionized physics and led to the development of quantum technologies that continue to shape the future. By revealing the inherent uncertainty in the quantum world, Heisenberg's principle forced us to rethink our understanding of reality itself, opening the door to new interpretations of the universe and new technological frontiers. Through its philosophical and practical implications, the uncertainty principle remains one of the most influential and transformative ideas in the history of science. Heisenberg's uncertainty principle is one of the most profound concepts in quantum mechanics, reshaping our understanding of the universe at its most fundamental level. The principle, introduced by Werner Heisenberg in 1927, asserts that there are inherent limitations to how precisely we can measure certain pairs of properties of a particle, such as its position and momentum, at the same time. This idea was revolutionary because it challenged the deterministic worldview that had been held for centuries. Classical physics, based on the work of Isaac Newton, believed that the universe was predictable if we knew the current state of all particles. However, Heisenberg's principle showed that at the quantum level, uncertainty is not a limitation of measurement but an intrinsic feature of nature itself. The uncertainty principle's core message is that the more precisely we measure one property such as the position of a particle, the less precisely we can know its momentum, and vice versa. This relationship is mathematically represented as deltax deltap greater than or equal to as 2, where delta is the uncertainty in position, deltap is the uncertainty in momentum, and n is the reduced Planck constant. This equation reveals that the more accurately we try to measure one property, the more uncertain the other property becomes. It shows that precision in quantum measurements comes at a cost. Achieving greater certainty in one aspect means sacrificing certainty in another. Unlike classical mechanics, where particles can be observed without disturbing their properties, in quantum mechanics, the act of measurement itself affects the system. One of the most profound implications of the uncertainty principle is its connection to wave-particle duality. The idea that particles, like electrons, can behave both as particles and as waves was proposed by Louis de Broglie and later confirmed in experiments. In the quantum world, particles are not localized objects with definite properties but are instead described by wave functions, which represent the probability distribution of where a particle might be found. When we measure the position of a particle, we force the wave function to collapse into a definite position, but this collapse disturbs the particle's momentum. The wave-like nature of particles means they do not have fixed properties until measured, and the uncertainty arises because we are trying to observe two aspects of a wave-like entity that cannot be precisely determined simultaneously. The uncertainty principle also challenges the classical concept of determinism, which held that if we knew the position and velocity of a particle, we could predict its future behavior. In classical physics, the idea was that the universe operated like a clockwork mechanism with precise laws governing the motion of all objects. However, quantum mechanics, through the uncertainty principle, introduced the idea that at the smallest scales, the universe is governed by probabilities rather than certainties. The principle shows that it is impossible to know both the position and momentum of a particle simultaneously, meaning that the future state of a system cannot be predicted with absolute certainty. Instead, we can only predict the likelihood of various outcomes, fundamentally altering our understanding of causality and time. The principle has significant philosophical implications as well. In classical physics, the universe was believed to exist independently of the observer, an objective reality that could be measured and understood. However, the uncertainty principle suggests that the act of measurement itself plays a crucial role in determining the state of a quantum system. This leads to questions about the nature of reality and the role of the observer. In quantum mechanics, particles do not have definite properties until they are observed, implying that reality is not independent of our perception. This challenges the classical view of an objective universe and suggests that observation itself shapes the physical world. This concept led to the development of the Copenhagen interpretation of quantum mechanics, which holds that the act of measurement causes the wave function to collapse into one of the possible states. The uncertainty principle also laid the foundation for the development of groundbreaking technologies. Quantum mechanics and the uncertainty principle have directly influenced the field of quantum computing, where quantum bits or qubits can exist in multiple states simultaneously. This ability to exist in superposition enables quantum computers to perform complex calculations much more efficiently than classical computers. Quantum computing has the potential to revolutionize fields such as cryptography, artificial intelligence, and materials science. In addition, quantum cryptography exploits the uncertainty principle to create secure communication systems. Since measurement in quantum systems disturbs the state of the system, any attempt to intercept or eavesdrop on a quantum communication would be detected, making quantum cryptography a powerful tool for ensuring privacy and security in digital communication. In conclusion, Heisenberg's uncertainty principle is not just a scientific concept. It is a fundamental shift in our understanding of the universe. By demonstrating that uncertainty is inherent in the quantum world and that measurement itself disturbs the system, Heisenberg challenged the deterministic classical view of the universe and introduced a probabilistic model that has since been confirmed by countless experiments. The principle's implications for wave-particle duality, determinism, and the role of the observer have profoundly influenced both science and philosophy. Furthermore, the uncertainty principle continues to shape the future of technology, with quantum computing and cryptography at the forefront of this revolution. As we continue to explore the quantum world, Heisenberg's discovery remains one of the most significant and enduring contributions to our understanding of reality. Heisenberg's uncertainty principle, introduced in 1927, has left an indelible mark on the world of physics and beyond. This principle, central to quantum mechanics, asserts that it is impossible to simultaneously measure certain pairs of properties of a particle, such as its position and momentum, with perfect precision. This realization shattered the classical worldview that the universe could be precisely known and predicted through measurements. The uncertainty principle did not simply suggest that our measurement tools were limited, but that uncertainty is an intrinsic feature of the universe at the quantum level. At its core, the uncertainty principle highlights a fundamental limitation of quantum mechanics. The principle is often expressed mathematically as del tax del tap greater than or equal to is 2, where del tax is the uncertainty in position, del tap is the uncertainty in momentum, and h bar is the reduced Planck constant. This equation shows that the more accurately we measure one property of a particle, the less accurately we can measure the other. For instance, if we measure the position of an electron with great precision, the uncertainty in its momentum increases. This is not due to a flaw in the measurement process, but is a direct consequence of the quantum nature of particles. In classical physics, such uncertainty did not exist. If you knew the position and velocity of an object, you could predict its future trajectory with complete certainty. However, in the quantum world, this is impossible. The uncertainty principle also ties directly into the concept of wave-particle duality, which was introduced by Louis de Broglie and later confirmed by experiments. Quantum particles, such as electrons, exhibit both particle-like and wave-like behaviors depending on how they are observed. When we try to measure the position of a particle, it behaves more like a localized particle, but when we measure its momentum, it shows wave-like behavior. This duality means that particles are not fixed entities with well-defined positions and momenta at all times. Instead, they are described by wave functions that represent the probability of finding them in a particular state. The act of measurement collapses the wave function into a specific state, but this collapse disturbs other properties, such as momentum, further highlighting the uncertainty inherent in quantum systems. Philosophically, Heisenberg's uncertainty principle has deep implications about the nature of reality itself. Classical physics was built upon the assumption of an objective, observer-independent reality. The idea was that the universe existed with fixed properties whether or not we were observing it. In quantum mechanics, however, the act of observation plays a crucial role in determining the state of a system. This led to the development of the Copenhagen interpretation, which proposes that particles exist in a superposition of states until observed, and only when we measure their properties do they collapse into a single, definite state. This shift challenged the classical notion of an objective, independent reality, and introduced the idea that reality is shaped by the act of measurement itself. This observer-dependent nature of reality has led to ongoing debates about the role of consciousness in the measurement process. The uncertainty principle also undermines the concept of determinism, a cornerstone of classical physics. In classical mechanics, the universe was thought to be deterministic, where every effect had a cause, and if we knew the exact position and velocity of every particle, we could predict the future with certainty. However, quantum mechanics, through the uncertainty principle, introduced a probabilistic view of the universe. Instead of being able to predict exact outcomes, we are limited to calculating probabilities. This is fundamentally different from classical physics, where the future was seen as a predictable extension of the present. In the quantum world, there is a fundamental randomness, and the future is not fully determined by the present. Despite the counterintuitive nature of the uncertainty principle, it has led to revolutionary advancements in technology. One of the most significant applications of quantum mechanics is quantum computing. Quantum computers use quantum bits, or qubits, which, unlike classical bits, can exist in multiple states at once. This superposition of states allows quantum computers to perform certain calculations exponentially faster than classical computers. The uncertainty principle plays a role in this by allowing quantum systems to exist in probabilistic states, which makes quantum computing possible. Similarly, quantum cryptography uses the principles of quantum mechanics, including the uncertainty principle, to create unbreakable encryption. Since measurement at the quantum level disturbs the system, any attempt to intercept or observe the transmission of information in a quantum system would be detectable. Heisenberg's uncertainty principle also played a crucial role in the development of quantum field theory, which describes the fundamental forces of nature. In quantum field theory, particles are not considered as isolated entities but as excitations or ripples in underlying fields. The uncertainty principle helps explain the behavior of these quantum fields, where fluctuations and uncertainty at the smallest scales are responsible for the creation of particles and interactions between them. These quantum fluctuations are a direct consequence of the uncertainty at the quantum level and are central to understanding phenomena like the Casimir effect, where the vacuum itself creates measurable forces between objects. In conclusion, Heisenberg's uncertainty principle has far-reaching consequences, not just for physics, but for our philosophical understanding of the universe. It introduced the idea that uncertainty is inherent in the fabric of nature, challenging classical notions of determinism and objective reality. The principle also laid the foundation for groundbreaking technologies, such as quantum computing and quantum cryptography, that are reshaping industries. Furthermore, it has led to ongoing debates in both science and philosophy about the nature of reality, observation, and the limits of human knowledge. Through its revolutionary insights, Heisenberg's uncertainty principle continues to shape our understanding of the quantum world and its profound impact on both theory and technology.